In this video, we're going to do some t-test calculations. They're not much different than the z-test, so you've got this. Let's take a look. So in this section, I'm going to talk with you about the logic of t-testing and the steps to calculate and some factors to consider when using a t-test. So there are three basic steps to computing a t-test. First, you're going to calculate the sample variance. You're going to estimate the standard error using that variance, and you're going to compute the t-statistic. So the first step is calculating the sample variance. Why do we have to do this? Because the population information is missing. And so if you will recall from an earlier lesson on calculating sample variance and standard deviation, instead of using n in the denominator of the formula, we use n minus 1, and we call this degrees of freedom. We do this to adjust the variance so that it more accurately represents what the variance would look like in the population. If you will recall, in the population, there will be more variance. There are more scores, there's going to be more spread. Samples tend to have less variance. And therefore, if we just take our sample variance and think that it's representative of the population, we're going to be wrong because the sample variance underestimates the population variance. So in other words, we say that there's bias in our sample variance calculation. So if you will recall, our variance formula was sums of squares divided by n, sums of squares being those sums of squared deviations. But in the sample variance, we say it's the sums of squares divided by the degrees of freedom, or n minus 1. So we make that small adjustment. And then our sample standard deviation, denoted with just a lowercase s, is the square root of those sums of squares divided by the degrees of freedom. Remember also that in this picture, it doesn't look like the square root symbol goes all the way over all the elements, but it does, so keep that in mind. The next thing we need to do when we're doing a t-test is to estimate the standard error. And we're going to substitute the variance in the formula for standard error. We're going to estimate the distance between our mean and the population mean. So when we were doing standard error before, we weren't estimating, we were saying this is the average distance between the mean and the population in terms of how means of populations vary. So, but since we are estimating our variance, now we have to estimate the standard error. We're going to compute some standard error, but we're going to say it's an estimate of what actually happens in the population. So our standard error formula, which used to have an S and a subscript E, will now have an S and a subscript M. And the formula is going to be a little bit different. It's going to be the square root of the variance divided by n. This is how we're going to estimate standard error for our t-statistic. So S subscript M is the square root of the sample variance divided by the sample size. Now you might be confused. You might say, well, why are we not using degrees of freedom here? Well, we already made the adjustment in our variance formula. We don't need to make the adjustment again in our standard error. So in our variance formula, we're going to have n minus 1 in the denominator, but in our standard error formula, we're going to have n in the denominator. So again, S subscript M is an estimate of the standard error. The estimated value is computed from sample data rather than the actual population parameter. We don't know the population standard deviation or the population variance, and so we're estimating it. So it's an estimate of the standard distance between any sample mean and the population mean. So we've got these unlimited means that can be drawn from a population and put on the distribution of sample means. There's a standard distance between those means and the distribution, and that's estimated using our estimated standard error. Okay, we're going to do a learning check, a couple learning checks right now. What I'd like you to do is go ahead and write down these 4 different scenarios, and then we're going to work them out together. So in the first scenario, for example, there are n people in the sample, And the sums of squares for the sample is 1,152. Now, if you don't remember what sums of squares are, I recommend that you go back to the chapter on variance and variability and take a look at how we determine the sums of squares. Okay, after you've written all these down, we'll go ahead and try to work some of them out.
Okay, let's start with this first question that we have. So we have an n of 9, and we have a sums of squares of 1,152. The first thing we need to do is find out the variance. And the formula for sample variance is right here. It is the sums of squares divided by the degrees of freedom. So let's do that first. Our sums of squares is 1,152. Our degrees of freedom are n minus 1, so this is going to be 8. So 1,152 divided by 8, you could pause the video if you need to figure it out, is 144. Okay, so we have the variance. That's good. Now we plug in our variance into our standard error formula, which is the square root of the sums of squares over the n. So I'm going to put my formula symbol here, and I'm going to take the square root of my variance of 144 divided by my total n, which is 9. And again, if you need to do the math, pause it, but 9 goes into 144 16 times. So we have the square root of 16. So our standard error in this case is 4. That's our standard error. Our estimated standard error, I should say. Okay, let's try another one. Okay, in this sample, we have an n of 25, and our sums of squares are 2,400. So the first thing we need to do is figure out our variance. And we figure out variance by dividing our sums of squares by our degrees of freedom. And degrees of freedom are n minus 1. So our sums of squares here are 2,400. Our degrees of freedom, n minus 1, is 24. So 24 goes into 2,400 100 times. So our variance is 100. Okay, now that we know our variance, we put it here. We take the square root of our variance divided by our n. So that's going to give us our estimated standard error. So I'm going to take my variance of 100. I need to put this all in a square root, divide it by my n of 25. 25 goes into 104 times, so I'm looking for the square root of 4. So our estimated standard error in this case is 2. All right, let's do another one. Okay, in this case we have an n of 36, and our sums of squares are equal to 1,260. The first thing I need to do is figure out my variance. My variance is my sums of squares divided by my degrees of freedom. Degrees of freedom are n minus 1. Sample variance is shown with an S superscript 2. So I have my sums of squares of 1,260 divided by my degrees of freedom, which is n minus 1, 35. And you can pause to do the math if you'd like, but I will tell you that that equals 36. So my variance is 36. Now that I know my variance, I can plug it into the formula for the standard error, the estimated standard error. So for the estimated standard error, I have the square root of my variance, 36, divided by my n, which was 36. So that is a square root of 1, and that means that my estimated standard error for this group is 1. Okay, we're going to try one more. Okay, for this last one, we have an n of 16 and sums of squares of 2,160. The very first thing I need to do is to figure my variance. And my variance is my sums of squares divided by my degrees of freedom, or n minus 1. So 16 minus 1 is 15. And do the math on that, and our variance is 144. So we have our variance, and now we can plug that into our formula for the estimated standard error. It's the variance divided by n, and take the square root of that. So I'll do that. I have the square root of my variance divided by my n of 16. Okay, so that is going to give me a square root of 9, which means that my estimated standard error is going to be 3. Hopefully this has been helpful.
So in case you missed it, in all of these calculations, we've been using variance and not standard deviation when we are calculating the estimated standard error. And previously with z-test, we used standard deviation. And sample variance in this case is unbiased. It's providing an unbiased estimate of the population. And we make it unbiased by having n minus 1 in the denominator. So those are two things to just keep in mind, that we're shifting into using variance in our standard error formula, and this variance is unbiased. All right, the next step is to compute the t-statistic. So the t is used as a substitute for a z-score test. And we do this because we don't know the population variance, and so therefore we can't use the unit normal table. So we're going to be using instead a t-table. So the only difference really in this formula from the z formula is that we're substituting that estimated error into our z-score formula. So the error that we were just computing in the last few moments. So our t-score is our mean of our sample minus the mean of the population divided by this new estimated standard error. So the only difference really is that standard error piece. And if we put it in words again, the sample mean is something we have from our data, minus our population mean, what we're hypothesizing, and the estimated standard error is computed from the sample data now. It used to be something we got from the population, but now we're computing it from the sample data. So these are the two formulas side by side, and you can just see that the very only difference is in that standard error. What used to be a population standard error is now an estimated standard error for the population based on what we're seeing in our sample. So therein is the difference. Okay, so I'm gonna present to you a problem. I'm gonna ask you to pause the video and try it and then come back for the answers. So a sample of 16 scores has a mean of 83 and a standard deviation of 12. And if you'll notice, I'm talking about standard deviation. You know we're going to use variance, so we got to figure out how to do that. So explain what is measured by the sample standard deviation, compute the standard error for the sample, and explain what is measured by the standard error. So those are your 3 tasks. Pause the video to try to figure it out, and then come on back. So what do we mean by the standard error? The sample standard deviation is an estimate of the population variance, and it's used to estimate the distance of the scores from the mean. So let's go ahead and dive in and figure out that estimated error. So if we have 16 scores with a mean of 83 and a standard deviation of 12, the standard error is going to be the square root of our variance divided by our n. Now, here is where it gets a little tricky. You weren't given the variance, you were only given the standard deviation. But if you will recall, the standard deviation is the square root of the variance. So when we're given a standard deviation, we can just square it to figure out the variance. So the standard deviation is 12, and our variance is the standard deviation squared. So 12 times 12 gives us 144. So we have the estimated standard error being the square root of the variance, 144 divided by 16, gave us a square root of 9, which means our estimated standard error is 3. And finally, estimated standard error is used as an estimate of the real population error. Because population standard deviation is unknown, it's going to equal the estimate of the difference between the sample and the population mean. So in other words, we don't really know what the standard difference is going to be of any sort of mean drawn from the population and the population mean. So we're estimating it. We're estimating it because we don't know the population standard deviation or standard or variance. Okay. In the next video, we're going to get into degrees of freedom, and I'm going to introduce you to this t-table. So I'll see you there.